Welcome to this last lecture on Introduction to Probability and Statistics. In this lecture, we will introduce you to the basics of hypothesis testing, which is an important activity when you want to make decisions from a set of data. So, to give you some motivation for hypothesis testing, we will look at some cases. Let us look at a business case where you are interested in investing in a mutual fund and you want to know whether this investment will yield a certain annual return greater than some desired value, let us say 15% or 20% that you might want. Now, this decision has to be made based on past performance of the fund, which you have data which you can collect. Similarly, let us assume you are a medical practitioner and you want to ask this question whether the incidence of diabetes is greater among males than females based on data that you have gathered about males and females and what proportion of males and what proportion of females have diabetes. Now, you can ask similar question in the social sector. You can, if you are a service provider, mobile service provider, you want to know whether women are more likely to change service provider than men, and depending on that you might want to provide more incentives accordingly for women to retain them. In engineering, you can ask a question such as a pump efficiency, if it has, whether it has degraded from its original value due to aging, and if so, you may want to do some maintenance of the pump. So, these kind of questions that or decisions that you have to make will be based on data that you have gathered about the particular object or item. Now, let us look at how do you perform these decision making using what is called hypothesis testing. Typically, what you have to do is to convert this hypothesis into a test for the mean or variance parameter of a population, or perhaps a difference in the means of two populations or a difference of variances of the two populations. The statement that previously we saw have to be first converted into a test of a parameter of some population. Now, this hypothesis is a postulate about the parameters. You call them either the null hypothesis or the alternate hypothesis. The null hypothesis is the default hypothesis that you want to test, the status quo postulate that you wish to reject if the sample set provides sufficient evidence. For example, this is the statement about which you want to make the strongest claim based on the data. So, that you choose as the null hypothesis and what we call the default hypothesis. Example, you want to convert this statement into a parameter called eta, whether this eta efficiency, let us say of the pump, is equal to eta naught, its original value. If you have per performance data that you collect, then you, based on the data you want to reject whether this efficiency at current time is different from its original value eta naught. If there is evidence, you will reject this hypothesis in favor of the alternative hypothesis, which is essentially saying that the pump efficiency in this case is less than eta naught. So, this is called the alternate hypothesis. So, you set up the hypothesis such as eta equals eta naught, which you call the null hypothesis, and the alternative hypothesis which you want to choose in favor of this if the evidence is there from the data, such as for example eta less than eta naught. So, all hypothesis testing has this null and alternative, and we can have different types depending on whether you are testing for the mean or the variance, and whether this is less than or greater than or on both sided, and we will see many such examples. Now, in order to perform this hypothesis testing and make a decision, as we said, the first step is to identify the parameter of interest which you wish to test. It could be the mean, it could be the variance of the population or the proportion of the population that you want to verify value. Now, you construct the null and alternative hypothesis as we said before. Then based on a data, experimental data about the system, you collect and then you construct something called the test statistic. This is a function of the observations. Now, this could be, for example, if you are testing for the population mean, you may use as the test statistic the sample mean. If you are testing for the population variance, you may use as a test statistic the sample variance, and so on and so forth. Now, you also have to derive the distribution of the test statistic under the null hypothesis. What it means is, if the null hypothesis is true, what is the distribution of this test statistic that you have computed. Now, based on this distribution, you choose a threshold or a test criterion, and now you compare the computed test statistic against this criterion and decide whether to reject the null hypothesis or not reject the null hypothesis. This is the overall procedure. We will show through examples how these procedures carried out for different cases. Now, you have to understand that the hypothesis testing procedure is an imperfect decision making process. Why? Because you are basing the test on a sample set of observations, not on the entire population. So, there are inherent errors in the hypothesis testing because it is based on observations which are themselves stochastic in nature. Now, therefore, the performance of the hypothesis test, how well this decision making performs depends on how much variability is there in the data. This you may not be able to do much about this. There might be enough sufficient variability in the data which prevents you from making a good decision. You can also alter the performance of the test by choosing the number of observations, experimental observations you want to make, which is called the sample size. Now, the test statistic, as we said, is a function of the observations. There are different, sometimes you might have different choices of functions, and some test statistic may actually perform better than others. That depends on the theoretical foundations of statistical hypothesis testing. We will not touch upon this. We have control over the number of observations. We will take a look at how we can alter the performance based on sample size. Finally, you also choose a threshold against which you are comparing the test statistic, and therefore you can alter the performance based on the criterion that you select, and we will see how this test criterion affects the performance of the hypothesis test. Now, there are two types of hypothesis tests, what we call the two-sided test and the one-sided test, and I am giving a simple illustration to tell you what a two-sided test means. Suppose you are testing for the population parameter mean, population mean mu, and you want to test whether this population parameter is equal to 0 or not equal to 0. So, the null hypothesis is the population parameter is 0, and the alternative is the population mean is not equal to 0. So, you observe some set of observations from this particular population. We have a sample and you have computed, let us say, a sample statistic, and let us also assume that sample statistic happens to be a standard normal variable z. We will show you how to construct a test statistic that finally has this kind of a distribution for testing the mean. But let us, for the time being, take it that we have a test statistic based on the observations we have made, and this test statistic that we have computed is a standard normal test statistic z. Now, we know that this z, because it is a standard normal distribution, will have some shape like this, and about 95% of the time the data, the statistic will have a value between around -2 to +2. Okay. So, for a two-sided test, we will say if the test statistic happens to be very large, we will reject it, or if it is very small, we will reject it. Why? Because if it is very large, it means it does not come from a distribution with mean 0. So, in this particular case, what we mean by very large, we can choose a threshold, let us say -2, I am sorry, +2, and if the statistic is greater than 2, we reject the null hypothesis, or if it is small, what do we mean by small? If it is less than -2, we reject the null hypothesis. So, in this case, we reject the null hypothesis whether the test statistic is less than a particular value, the threshold value. In this case, I have chosen the threshold as -2, and or if the statistic is greater than the threshold value, which is +2. So, there are two thresholds, the upper threshold which is 2 and the lower threshold which is -2, because it is a two-sided test. We want to reject the null hypothesis if mu is less than 0 or mu is greater than 0. How we choose these thresholds and what are the implications, we will see later. But realize that if it is a two-sided test, you basically have a lower criterion threshold and the upper threshold, which you select from the appropriate distribution. Now, suppose you have the same thing, but you are only interested in testing whether the mean is 0 or greater than 0. So, in this case the null hypothesis is mu equals 0 and the alternative is mu less than 0 or greater than 0. So, notice that mu equals 0 implies that you are also willing to, you are not interested in the case when mu is less than 0. You are not going to reject the null hypothesis if mu is less than 0. You are going to reject the null hypothesis only if mu is greater than 0. That is why you have written the alternative like this. This is called a one-sided test. In this case, let us assume that you again have computed a test statistic based on the observations, and that is a standard normal test statistic. Then we only have an upper threshold. Okay. So, because we want to reject the null hypothesis only if the mean is greater than 0. So, similarly, if the statistic is greater than a threshold, then we reject the null hypothesis. So, we have a upper threshold, in this case I have chosen 1.5 and reject the null hypothesis if the statistic happens to be greater than 1.5. If it has a low value, we are not bothered, because we are not bothered when mu is less than 0. So, although technically we should call the null hypothesis mu less than or equal to 0, it is usually stated as an equality as mu equals 0 with indifference. Essentially the alternative tells you whether we are indifferent to mu less than 0 or not. Okay. So, this is called a one-sided test. So, depending on the type of test, whether it is two-sided or one-sided, you choose thresholds and then compare the test statistics against those thresholds. Now, when you do such a test, you commit two types of errors. So, essentially let us look at this truth table. Suppose the null hypothesis is actually true and you have made a decision to not reject the null hypothesis, which means you have made the correct decision. So, this will not happen all the time, because your sample is random. It is possible that even if your null hypothesis is true, you may conclude that the null hypothesis, you may decide to reject the null hypothesis, in which you commit a type 1 error, what we call a type 1 error or a false alarm. So, when the null hypothesis is true and then you reject the null hypothesis based on the sample data and your statistic and the threshold you have selected, we call this a type 1 error or a false alarm, and the probability of that is known as alpha, and we will call it a type 1 error probability. So, you will have, it is not that your decision is perfect, you will always commit some type 1 error alpha depending on the threshold that you have selected and the statistic you have computed. Similarly, let us assume that the truth is that the alternative is correct. Okay. So, in this case it may turn out that from your sample set of data you do not reject the null hypothesis, in which case you commit what we call a type 2 error, and this type 2 error also has a probability which is denoted by beta. On the other hand, if the alternative hypothesis is true and you do reject the null hypothesis in favor of the alternative, then you have made a correct decision, and that correct decision probability is known as power of the statistical test and is denoted by 1 minus beta. Remember, the only one of two decisions you are always going to make. You are either going to reject the null hypothesis or you are not going to reject it. So, the total probability will always be 1, and the probability of type 2 error, if it is beta, then the probability or statistical power is 1 minus beta. So, there are two types of errors that you commit, what we call the type 1 error probability alpha and the type 2 error probability beta. So, the type 1 error probability alpha is also known as the level of significance of the test, and this is typically what you control. You do not control the type 2 error probability. When you construct this hypothesis test, construct the test statistic and choose a threshold, you basically try to control this type 1 error probability. The type 2 error probability results as a consequence of this. So, we will choose the criteria from the distribution of the test statistic under the null hypothesis, because the null hypothesis is very precisely stated. If you go back and look at it, we are able to state the null hypothesis precisely. The parameter value is 0, whereas the alternative hypothesis, we do not know what the parameter value. We entertain a huge set, mu not equal 0 involves everything other than 0. So, the parameter set is undefined, very not clearly defined, at least exact value is not clearly defined in the alternative, whereas for the null we are clearly defined in both cases. Therefore, it is possible to construct the distribution of the test statistic under the null hypothesis, and that is the reason we only end up controlling the type 1 error probability and not the type 2 directly by choosing the test statistic. Now, let us see how we actually control the type 1 error probability for the by choosing the appropriate test statistic value, test criterion value. So, let us look at the qualitative comparison of the type 1 error and type 2 error. Let us assume that under the null hypothesis you have this distribution which is known as distribution of the test statistic under H naught. Now, depending on, remember that even if H naught is true, the statistic can have a value between minus infinity to plus infinity. On the other hand, you are going to choose some threshold. I have indicated this by this vertical line. You are going to choose some threshold, because you can't say that you will accept, you will not reject the null hypothesis whether the value is any value between minus infinity and plus infinity, in which case you will never reject the null hypothesis whatever be the evidence you get. That is not fair. You decide to reject the null hypothesis, let us say in this case a one sided test, and you have decided to reject it if the statistic exceeds this threshold value, in which case notice that when the null hypothesis is true, this test statistic can have a value greater than this threshold, and the probability that it can have a value greater than the threshold is indicated by this blue area. So, this is your type 1 error probability that you are committed. Okay. If the null hypothesis is true, your test statistic can exceed this threshold, in which case this is the area, the probability that the test statistic can exceed this threshold, and therefore this is your type 1 error probability. Now, if you move the threshold to the right, obviously you can reduce your type 1 error probability, but there is a price to be paid. Let us look at what is the price. Let us look at what happens to a type 2 error probability. So, let us assume that the actual distribution of the test statistic under H1, under the alternative, happens to be this kind of a distribution. Of course, this depends on what value the parameter is going to take. Suppose we consider this distribution as the distribution of the test statistic if the alternative is true. Then what happens is, there is a probability that the test statistic will take a value less than this threshold, and that is given by the probability marked in red, which means that even if the alternative is true, you will not reject the null hypothesis because your test statistic is falling to the left of this threshold, and the probability that the statistic will be left of the threshold is given by the red area, and that is going to be your type 2 error probability, and the power is just 1 minus this, which is the area to the right of this under this distribution under H1. Now, notice that as you move the threshold to the right, the blue area shrinks, which means your type 1 error shrinks, but your red area increases, which means your type 2 error increases. So, there is a trade off. If you try to make your test perfect in the sense of no type 1 error, then you will commit a type 2 error of 1, which means you will be a very insensitive test. You will never be able to find whether your mean is different from 0, for example. So, the less type 1 error you are willing to entertain, the less sensitive your test will be. So, there is always a trade off, you can't help it. So, there is a trade off. If we decrease type 1 error probability, then type 2 error probability will increase, there is no choice, and you have to accept this trade off. So, you decide that I am willing to accept a type 1 error probability of 1% or 5% or 10%, and accordingly your test will be less or more sensitive. Okay. This is the way. The threshold selection is based on how much of false alarm probability or type 1 error probability you are willing to accept, and that is the trade off you should accept, and accordingly your test will be less or more sensitive. Now, let us look at some examples for hypothesis testing. In this case, we have looked at a manufacture of a solid propellant, and we want this solid propellant to burn at a certain rate, and this burning rate of the solid propellant is specified to be, let us say, 50 cm per second. If it burns at a higher rate, then we will not be able to control the rocket. If it burns at a slower rate, then the rocket may not even take off. So, we are going to check whether the propellant we have made, which is based on mixing a lot of different chemicals, whether it will have a burning rate of 50 centimeter per second. Now, what we have done from the mixing bowl where we are making the solid propellant, we have taken 25 samples from different locations in the mixing bowl, and each of these samples we test in the lab and find that what their burning rate is, and it will be some value, maybe it is 48, 49, 51, whatever. So, we compute the average of these 25 samples. Notice that the population parameter mean that we are testing is mu equals 50, and we are going to use the sample mean. We have taken 25 samples, we compute the average or the sample mean of the burning rates of these 25 samples, and we are going to make a judgment about the entire batch that we are making in the mixture, remember. So, the population in this case is the entire batch of product that you are making, and you have taken only a few samples, and based on these samples you are making a judgment about the entire batch. So, the population parameter mean mu is what you are interested in. You do not know what its value will be, you are going to ask this question whether that mean is going to be 50. The sample mean that you have computed based on these 25 samples happens to be 51.3 centimeter per second, the burning rate average value. We have also computed the standard deviation based on these 25 samples. We can compute the standard deviation of the sample, and we find that the standard deviation is 2 centimeter per second. So, different samples have different burning rates, and we find that the variability or the standard deviation in the burning rate of the samples is 2 centimeter per second. Now, based on this data that we have collected, the sample mean and the sample standard deviation, we want to ask the question whether the population mean happens to be 50 centimeter per second. I am sorry, let us say that the sample standard deviation is already known to you, given to you that it will be 22 cm per second. It is not based on the sample, it is already known to you. Let us take that as a case, which is the simplest case. So, here we have actually set the null hypothesis as population mean having a burning rate of 50 centimeter per second, and the alternative is mu not equal to 50. Notice it is a two-sided test because we want to reject this batch if the burning rate is less than 50 centimeter per second, it is not useful to us, or if it is greater than 50 centimeter per second. That is why we have taken the alternative to be not equal to 50 centimeter per second. Now, this is a two-sided test. Now, how do we construct the test? I already talked to you that the sample mean has a normal distribution with population mean as the parameter, the expected value, and the standard deviation of the population divided by square root of n. You can refer to the previous lecture to find out that the distribution of x bar, the sample mean, is the same as the population mean and has a standard deviation which is standard deviation of the population divided by the square root of the number of samples you have taken. So, we can now do what is called standardization, which is subtracting the mean of the sample mean, which is 50, the expected value, divide by the standard deviation of the sample mean, which is 2 by root 25, and we get what is called the standardized value, and this standardized value z will have a standard normal distribution with 0 mean and unit variance. Now, notice that this will be the distribution if the population mean happens to be 50. That means under H naught, under the null hypothesis, the test statistic will have a standard normal distribution. Now, we know that 95% of a standard normal variable will lie between plus or minus 2 standard deviation approximately. More particularly, the standard normal variable will lie between plus or minus 1.96 95% of the time. So, if you are willing to tolerate a type 1 error probability of 5%, let us say, which means what you are saying is the area that you have on the left plus the area that you have on the right of the upper threshold is equal to 5%. If you are willing to tolerate that type 1 error probability, then you can choose your criterion or your threshold as 1.96 and minus 1.96, and that is exactly what is stated here. The threshold value is plus or minus 1.96, and if your z statistic happens to be greater than 1.96, you reject it. If it is less than minus 1.96, you reject the null hypothesis. In this particular case, if you substitute the value of the x bar that we have obtained, which is 51.3, and we have this standard deviation which you already know, and we compute this, we get a value of 3.25 which is greater than 1.96, and therefore we reject the null hypothesis. This batch does not satisfy our needs. So, this is the way of testing, and this is an example of testing for the mean given the standard deviation of the population. In case your standard deviation of the population is not known, then you use the sample standard deviation, and this test statistic we can show is a t statistic, and therefore you can derive your thresholds from your t distribution rather than the z distribution. Okay, let us look at another example where we are testing for difference in means. Here we have two groups of teachers. This is a social example. So, we have two groups of teachers of let us say similar capabilities. There are 10 teachers in each group, and we have trained them by two different methods, A and B teaching methodology. Now, we want to know whether method B is more effective than method A. Now, let us we assume that we have 10 teachers in each group, we have given training for one group of teachers using method A and another group of teachers using method B, and then we test them for the effectiveness and we find their scores. We find that the average scores of group 1 happens to be 70 with a standard deviation in the marks is 3.37, and group 2 has a sample mean of 74 with a standard deviation of 5.4 approximately. So, we want to know whether method A and method B are both equally effective or method B is more effective than method A. This is the question that we want to do. So, we have chosen the null hypothesis that method A mean and method B mean both are equal, which means the difference in the mean should be equal to 0. That is your null hypothesis. We will reject this in favor of the alternative, which says the average, the effectiveness of method A is less than the effectiveness of method B, which means the mean of method A is less than the mean of method B, which means the difference should be less than 0. Notice that it is a one sided test, because we are not interested in looking at whether method A is more effective than method B. We are only asking the question, is method B more effective than method A, and we are setting up our hypothesis accordingly. The difference in means equal to 0 happens to be the null hypothesis. The difference in means 1 minus 2 is less than 0 is the alternative we will choose in case we find enough evidence for rejecting the null hypothesis. Now, we will assume that the standard deviation of these two groups is same, although we do not know the standard deviations. Okay. So, we will make the assumption that the standard deviation of marks obtained by group A population and the standard deviation of the group B population of teachers are equal but unknown. Okay. But however, we have the sample standard deviations from these two groups, from which we can estimate the standard deviation of this entire group of teachers. Notice that all the teachers, I can group them because they have the same variability. There is no difference in the variability of group A and group B. So, we can pool their variances and we can obtain a pooled variance by just taking the sum squared deviation with the respective means and then obtaining a pooled variance. This is the way by which you obtain the pooled variance for two groups, and once you have obtained an estimate of the standard deviation of the group of teachers, then you can take the difference in the sample means, because remember you are testing the difference in means. So, you can take as the test statistic the difference in the sample means x1 bar minus x2 bar divided by the variance standard deviation of these means, which is what this is all about. So, SP represents the standard deviation of the difference in the means, remember assuming that we have both the groups have the same variances. So, now we can show that this particular statistic we have computed is a t statistic, because sigma is also estimated from the data. So, we can now compare this with the t distribution. The number of degrees of the t distribution happens to be n1 plus n2 minus 2. Notice that depends on the denominator degrees of freedom, which is essentially total number of observations minus two parameters which are mean parameters that you have used up to estimate the means. So, the remaining degrees of freedom is this, and that is how this number of degrees of freedom comes about. In fact, for large enough n1 and n2, if you take large enough n, you can actually approximate this with a standard normal variable. But in this case, let's do a precise job. We will choose the test criteria from the t distribution with this many degrees of freedom, 10 plus 10 minus 2, which is 18 degrees of freedom, and we find that the one sided confidence interval, remember this is one sided, if we are willing to tolerate a type 1 error probability of 5%, then there is only a lower threshold because less than 0, notice. So, minus 1.73, the probability that the t distribution with 18 degrees of freedom is greater than this minus 1.73 will be 5%. So, if we are willing to tolerate a type 1 error probability of 5%, then we can choose the threshold value as minus 1.73 drawn from the t distribution with 18 degrees of freedom and compare it with the statistic. The statistic itself we compute by plugging in the value for x1 bar, x2 bar and so on and so forth, we get minus 1.989. Since this is less than minus 1.73, we reject this null hypothesis in favor of this alternative, which means method B is more effective than method A. That is the conclusion. So, let us look at another example, which is a test for difference in variances. Now, we have two processes which have different variability, and we want to compare whether these two processes have the same variability or not. So, we have taken 50 samples from each process and computed their variances and found that one has a variability of 2.05 and the other has a variability or a variance of 7.64. Now, what we want to compare is whether these two variances, population variances of these two processes are equal or not, which means the ratio of the variances we want to check whether it is equal to 1 or not. The alternative hypothesis is that the variances are different. So, we are asking whether the ratio of the variance is not equal to 1. It could be that sigma 1 squared is less than sigma 2 squared or sigma 1 squared is greater than sigma 2 squared. Both cases we want to reject the null hypothesis. So, this is a two-sided test. Again, we can use the ratio of the sample variances as a test statistic, and this ratio turns out to be an F distribution with degrees of freedom n1 minus 1 and n2 minus 1, where n1 and n2 represents a number of samples we have taken for each of the process. In this case, we have equal number of samples we have taken. Even if you have taken unequal samples, we can appropriately choose the degrees of freedom for the F distribution and compare. So, in this case, if you plug in the values for S1 squared, S2 squared, we have got a F value of 0.27, and if you go to the F distribution with n1 minus 1, which is 49 degrees of freedom, and n2 minus 1, which is 49 degrees of freedom, and ask 5% probability, okay, which we break it up as 2, left of the threshold should be 2.5% and greater than the threshold is 2.5%. So, we ask what is the lower threshold value for the F distribution, and it turns out to be 0.567. That means 2.5%, there is a 2.5% probability that this F distribution is less than this value, similarly under H naught, and similarly there is a 2.5% probability that the F distribution is greater than this value. So, the lower threshold we choose as 0.567, upper threshold as 1.762. The statistic we have computed happens to be less than this. So, we reject the null hypothesis in favor of the alternative and claim that the two variances of the two processes are not equal. Of course, although this implies that the process 2 has a higher variability, if you really wanted to test this and not worry about process 1, then we would have set it up differently, the hypothesis testing. In summary, I want to just go over some of the standard tests that we use in hypothesis testing and see where they are useful. So, the z test or the standard normal variable statistic which has a standard normal variable, we call it a z test, and this is typically used for testing of the mean or a comparison between two means when the variance of the population is known. The application of such a test is usually found in testing whether the coefficient of a regression, linear regression model is 0 or not. Now, the t-test on the other hand is used also for a test of the mean or a comparison between two group means, but in this case the population variance is not known. So, we use the sample variance for normalization and that gives rise to a t-test. Here also whenever we test for the coefficients of the regression model under the assumption that the errors corrupting the variables, we do not have an idea, the way standard deviation of the errors that corrupt the observations are unknown, then we use the t-test and to test whether the coefficient of a regression model is equal to 0 or not. The chi-square test is used for testing the variance of a sample, and the variance of a sample is this test is used to test whether a regression model is good or not, whether of acceptable quality or not. The objective function of a regression model is a sum squared term and is similar to a variance, and you can use it to this chi-square test to test whether the regression model is acceptable or not. The F test is used when for comparing variances of two groups. In the case of linear regression, this is used to choose between two regression models having different number of parameters. Sometimes you might actually build a model by dropping a variable and you want to know whether the model you have built by reducing the number of variables is better than the one that by retaining all of them. In such a case, this F test comes in very handy. We have completed the introduction to probability and statistics. We will see you in the next lecture, which will talk about linear regression and the application of these concepts to linear regression. Thank you.